In this PowerPoint, I'm going to cover how to differentiate sine, cos and tan. So the first thing I want to show you is just a rough idea of how to differentiate sine. It's not a rigorous proof, but I think it's a nice way of giving you an idea of how to differentiate sine. So first of all, I've put the picture of the sine graph. I've just gone from 0 to 540. Obviously I could have gone on further. And underneath, I'm going to try and draw a graph of what the gradient is doing. Because remember that when you differentiate, that's what you're doing. You're finding the gradient. So underneath, I'm going to try and draw a graph of what the gradient of this sine curve is doing. So I'm just going to mark off some numbers, some reference points. Now I'm going to start off with points that I think are quite easy to plot, and I'm going to start off with this one at 90 degrees. If I drew on a tangent at 90 degrees, that tangent would be flat. So the gradient of the curve there is 0. So at 90 degrees, I'm going to plot that gradient there as 0. So the y-axis is shown where the gradient is. Now the next point that I'm going to plot is 270. Because that's another point where if I drew on the tangent, it's flat. So at 270, the gradient is 0. And then the other obvious one on this picture is 450. Again, the tangent there becomes flat, so the gradient at 450 is 0. Next, I'm going to start looking at some bits in between those points that I've plotted already. I'm going to do it in little chunks. Let's have a look at this part here in yellow, so between 270 and 360. Between 270 and 360, if I drew on tangents, I can see that those tangents would be positive, and as I move along the curve, they'd be getting steeper and steeper and steeper. So the gradient there is positive and it's getting higher, and the highest it reaches is going to be when it's at 360 degrees. So my gradient there is increasing, becoming more and more positive. The highest point it reaches will be at 360. So in this section, the graph gradient is increasing and it reaches its highest point at 360. Next, I'm going to look at this green part of the graph, which is between 360 and 450. Now in that region, the graph is still moving upwards, so it still has a positive gradient. And if I drew tangents on, they would still have positive gradients, but they're becoming flatter and flatter and flatter. So even though they're still positive, they're approaching 0, they're getting smaller. So that curve is going to come back down to 0. Right, next I'm going to look at this bit of the graph that I've just coloured in blue. In that part of the graph, the gradient started at 0, I've already drawn that tangent on, that's flat, and now if we started drawing tangents as we come around this curve, they start becoming negative. As we go along the curve, they become steeper and steeper and steeper, they become more and more negative, and the steepest it will become will be at 540, so that's when it's at its most negative value. So it's becoming negative and it's becoming more negative. So that shape is going to do something like this. Now I could keep doing that with each little section of the graph, and if I carried on following that idea, I'd end up completing my picture and it would look something like this. Now I'm hoping that you're looking at that graph and you're recognizing that shape. We've seen that shape before. This is the shape of the cos graph. So what I've shown you there, very roughly, is that when you differentiate sine of x, you get cos of x. Now in the booklet there's a much more rigorous proof of that, which is the proof from first principles. And if you're asked to prove this in an exam, which you might be, then the proof from first principles is a much better proof that you should use. So on the next slide now I'm going to go through that rigorous proof of that sine of x becomes cos of x when you differentiate it. So this is the proof that's printed in your booklet, and there are a couple of things that are going to be used in this proof, which I want to point out first of all. In the trigonometry booklet, we learned that there are some small angle approximations which are just printed here at the top. Sine x is approximately equal, theta, sine theta is approximately equal to theta, and cos theta is approximately equal to 1 minus a half theta squared. So those are the small angle approximations that we proved in the trigonometry booklet. Right, so let's have a look now at this proof. So starting here. So f of x equals sine x, and we want to differentiate it. Now when we're using the differentiation from first principles, the formula that we start with is the limit as h tends to 0 of f of x at h minus f of x all over h. So that's the first principles formula that you learned at AS. So if we apply it to this function, we'll have sine of x plus h minus sine of x all over h. So that's going to be our starting point. Now on the next line, we can expand sine of x plus h using the compound angle formulae from the formula booklet. So I'm talking about the sine A plus B formula. So hopefully you remember seeing that in the formula booklet. You will have covered that in the trig topic. So it's the sine of A plus B formula from the formula booklet. And rather than A's and B's, we've got X's and H's. So in the formula booklet, it will say sine A cos B plus cos A sine B, but we put in our X's and H's. So we have sine X cos H plus cos X sine H. The other sine X on the top, let's just leave that there for a minute, and then the H on the bottom, again, let's just leave that there for now. Now, the next thing that we can do is on the top, we can do a bit of factorising, because some of the terms have a common factor. If we look at the sine x cos h and then the minus sine x, they have a sine x in common. So for those two terms, we can factorise out the sine x, and then that will leave cos h minus 1. The cos x sine h, we'll just leave that as it is for now, so we'll leave that alone, plus cos x sine h. Now the next step is to split up this big fraction into two separate fractions. So we've got the sine x brackets cos h minus 1 over h, so that could be one fraction. And then the cos x sine h over h, that could be a separate fraction. And if we're splitting it into two separate fractions, we could write the limit twice. So we could write the limit as h tends to 0 on the first fraction, and then the limit as h tends to 0 on the second fraction. Now on the next part, all they've done there is they've taken the stuff without h's outside of the limit, because if they don't involve h's, they're not going to change when we change the h, so it doesn't really matter whether they're inside or outside the limit. So that sine x could be taken outside of the limit, and then this cos x could be taken outside of that limit. So then we end up with this sine x limit cos h minus 1 over h, and then the other one is cos x limit sine h over h. Now on the next part in the booklet, they've jumped straight into this last bit. What they've done here is they've used the small angle approximations. They've called it small angle estimations. So if theta is really small, we're using h here, so if h is really small, sine of h is approximately equal to h. So they've used there sine of h is approximately equal to h. And when we substitute that in there, we end up with h over h, which is just 1. So that's why you can see that 1 there, cos x times 1. We don't even need to put a limit in because there's no h left. It's just h over h, which is 1. H's there have disappeared. The other fraction, this one, they've put in the small angle approximation for cos h. They've said that cos h is approximately equal to 1 minus half h squared. So they've put that in there. They've subtracted the 1 and divided it all by h. And they haven't really shown much work in, so I'm going to do that on the side. So the cos h minus 1 over h, they've put in the small angle approximation for cos h. So that's 1 minus half h squared minus this other one all over h. The 1 and the minus 1 on the top cancel each other out. And minus a half h squared divided by h is minus a half h. So we end up there with this being minus a half h. But then, if we set the limit as h tends to 0, as this tends to 0, minus half h will tend to 0. So it'll end up being sine of x times 0. And that's why you can see that 0 there. So last step then, sine of x times 0 is nothing, so we can ignore that bracket. Cos of x times 1 is cos of x. So our final answer is cos of x. So we have shown that if you differentiate sine x, you get cos x. The other bit on this key point at the bottom is that if you differentiate cos x, you get minus sine x. You can prove that in the same way. So if you wanted to do the proof that cos becomes minus sine, you could go through this exact same proof, following all exactly the same steps, same method, but you're just starting with cos instead of sine. Then you should end up with an answer of minus sine of x. Let's go back to that graph idea, just so that I can show you that cos does become minus sine. Remember, this is not a rigorous proof, it's just to give you an idea so that you can see hopefully what's going on. So I'm drawing here a graph of what the gradient of the cos graph's doing. So I've printed the cos graph on the top. And let's plot now what the gradient's doing. I'll start off with points that are easy. So here, you can see the gradient's flat. So the gradient of that point is 0. The other points where the gradient becomes flat is 180 and 360. So 180 and 360, the gradient is 0. Right, now I'm going to start looking at some different chunks of the graph. I'll start off with this chunk here, between 180 and 270. In that chunk, the gradient is increasing. It's gone from 0 and it's getting higher, because if I kept drawing tangents going along this curve, those tangents would get steeper and steeper and steeper, and the steepest they would get would be at 270. So the gradient between 180 and 270 is positive, it's getting higher, and it reaches its peak at 270. Then, between 270 and 360, the gradient's still positive, still travelling upwards, but it's getting lower, it's getting flatter, and it comes back down towards 0. So the gradient is still in the positive region, but it's coming back down towards 0. Let's have a look at this blue part next. So the blue part is between 360 and 450. Here now the gradient starts becoming negative. It started from 0 and then it's going down and down and down, and the steepest it gets is at 450. So the gradient's negative, and the steepest it gets, so the most negative value is at 450. Now I could keep doing that for each little chunk of the graph, and if I did, I would end up with a picture that looks a bit like this. So you can see there that this looks like a familiar graph to us. It looks a bit like the sine curve, but it's upside down, because the sine curve, we do it in dotted, sine curve goes that way, doesn't it? So it's a reflection of the sine curve, and when you reflect a graph in that way, it's the negative of the function. So that graph that I've plotted very roughly is the negative sine x graph. So when you differentiate cos, you get minus sine. So these are the facts you need to memorise. When you differentiate sine, you get cos, and when you differentiate cos, you get minus sine. Here are some more questions, which we'll go through. These are a little bit more complicated. So on this first one, it's sine of 3x. Now when you differentiate sine of something, it becomes cos of something. So the first thing I'm going to write down is cos of 3x. But that's not the whole story, because we need to employ here the chain rule, which is where we not only differentiate the sine part, but we also differentiate the 3x part. And if you differentiate 3x, you get 3. So I've got to times this whole thing by 3, which I'm going to put in front. So sine became cos, and I've times by the differential of the bracket. That's the chain rule. Now the 4x to the 5, don't forget the normal rules that you learned last year for differentiating. With a polynomial, you bring the power down, 4 times 5 is 20, you take one off the power. Okay, moving on to the second one. Now when you differentiate cos, it turns into minus sine. So this is going to become minus 4 sine 2x, but then don't forget I'm also going to times by the differential of the bracket. So it's going to become minus 8 sine 2x. Let me say that bit again. Cos becomes minus sine, so that's why there's a minus and a sine. And if it's cos of 2x, it'll be minus sine of 2x. Originally there was a 4 there, but I'm timesing as well by the differential of the bracket. So that 4 doesn't stay as a 4. 4 times 2 is 8. The second bit of the question, don't forget that root is the same as power of a half. So if I want to differentiate that, it would be a half x to the minus a half. So that's just a reminder of what you learned last year. Okay, moving on to the third one. When we differentiate cos, we get minus sine. So that must mean that if I differentiate minus cos, I get positive sine. So negative cos becomes positive sine, and then I times by the differential of the bracket, which this time is 5. So I left a little gap there because I knew I was going to put in that 5. Now the next one is x sine x. So this now is a product. So I'm bringing back that product rule again. Differentiate the first bit. If I differentiate x, it's just 1 times with the second part, which is sine x, plus differentiate sine x, which is cos x, times by the first function, which is x. So I'm going to write that as sine of x plus x cos of x. So I differentiated the first one times with the second, plus differentiate the second one times with the first. Right, for the last one, I would rewrite this question. Instead of sine cubed of x, remember that this is the same as sine of x, all cubed. So just like when we did brackets with powers, if you want to differentiate this, you can bring the power down in the front, then you take one off the power, and then you times by the differential of the bracket. So I'll say that one again. I've got the 3 down in front, I've taken one off the power, and then I've times by the differential of the bracket. That's the chain rule part, When you differentiate sine, you get cos. Right, press pause now and have a go at these questions on the right hand side. I'm going to write in the answers soon, so make sure you press pause now. Okay, so we've differentiated sine and cos. Now we're going to move on to tan. So to differentiate tan, we need to think about what we know about tan already. From last year, you should know that tan of x is the same as sine of x over cos of x. And that fact comes in really handy because not only do we know how to differentiate sine x and cos x, but we also know how to differentiate them like this in a fraction because we could just use the quotient rule. So I'm going to use the quotient rule, which is where I differentiate the top and times with the bottom, minus differentiate the bottom times with the top, all over the bottom squared. So let's go through that in stages. I'm going to differentiate the top. If I differentiate sine x, I get cos x. I times it with the bottom, so there's the other cos x, minus differentiate the bottom. Well, when you differentiate cos x, you get minus sine x times with the top. So that's where the other sine x's come from. And then it's all over the bottom squared. So cos of x all squared. Next, we could simplify the top because instead of writing cos x, we could just write cos squared x. Same with sine x. And then in between, I've changed the minus into a plus. Now, hopefully you can think of a way of simplifying that bit on the top. Cos squared plus sine squared always equals 1. Because the x's match, cos squared x plus sine squared x always equals 1. So this is 1 over cos squared x. Now, that's looking quite simple as it is. So we could potentially leave like this, but there is another way of writing this because we've given this year a special name to 1 over cos. This year, when you did the trig booklet, you will have defined a new function as 1 over cos, and the thing that we called 1 over cos was sec. So 1 over cos squared is the same as sec squared. So we've just proved that when you differentiate tan of x, you get sec squared of x. And this one is in the formula booklet, so don't worry if you forget it. If you differentiate tan, you get sec squared. It's in your formula booklet. So let's do a couple of examples. We know that when you differentiate tan, you get sec squared. So if it's tan of 3x, you'll get sec squared of 3x. And then don't forget that chain rule. you also have to differentiate the 3x, which is 3. So I'll slot that in the front. So my final answer is 3 sec squared 3x. This second one, I'm just going to rewrite the question. And I'm just going to put the cubed on the outside. And for me, that makes it easier to differentiate. So this time I'm differentiating a bracket with a power. So first of all, I'll do what I normally do with a bracket with a power, which is I bring the power down in front, and then I take one off the power, so that power will go down to a 2. And then I times by the differential of the bracket. So now I've got to differentiate tan of 4x. Well, I know that when I differentiate tan, it becomes sec squared. So tan of 4x becomes sec squared of 4x. But I also need to times by the differential of the bracket, which is 4. So there's a lot going on in that question. Let's see if we can write that in a nicer way. 3 times 4 is 12. And then I've got a tan squared of 4x and also the sec squared of 4x. So have a go now at some questions from the booklet. Press pause and have a go at these ones. Look out for the questions now with the tan in.